I mean, drinking a bottle of whiskey takes a little more time.
So another question. Come on, guys.
As you know, there's in the press sometimes called the Higgs boson the God particle. What do you think of that?
Well, that I mean, drinking a bottle of whiskey takes a little more time.
So another question. Come on, guys.
As you know, there's in the press sometimes called the Higgs boson the God particle. What do you think of that?
Well, that embarrasses me. I mean, the term God particle was introduced by Lederman in his book, and Lederman claims that he didn't really intend that to be the title. He wanted to refer to it as that goddamn particle, and his editor wouldn't let him, so he just abbreviated it to the God particle. But I find it embarrassing because although I'm not a believer myself, it's a sort of misuse of terminology which I think might offend some people.
In Biederman's book, he compares the Higgs mechanism to the Tower of Babel, which is to say that in the early stages there was this beautiful incandescent symmetry, and then as things cooled, the Higgs mechanism came and made a mess of things. And I think that's why he calls it the goddamn particle, because he feels it's what separates us. Yeah.
Well, it's a curious point of view, I think, because I mean in the early universe, going through the phase transition in which the symmetry breaks, and in which the Higgs mechanism then operates, is actually producing, in a sense, a more ordered structure, which makes so many things possible. We wouldn't be here without it, because it's separating out electromagnetic long-range forces from.
You've actually been to see how you felt around the various places where you've been at CERN, and also how long is it since you've actually visited CERN, and what's your impression of how it has changed? Obviously, partly as a result of experiments in order to back up your theories.
Well, I'll answer the second part first. The last time I was at CERN, it was a very brief visit to see a colleague's experiment in the north area at Presse. That was 1985, and I was only here at CERN for an hour or two, so I really didn't form much impression of how the site had developed then. The previous occasion was at a conference in 1979, where I did see more, but at that stage the exciting thing was the hole in the ground in which the anti-proton accumulator was to be built to get Carlo Rubbia his Nobel Prize. But my main visit to CERN in terms of time was as long ago as 1976, and certainly over the years the growth of the area covered and the density of the buildings has been tremendous. I find it difficult to find my way around. There are only one or two places that I still recognise, like the cafeteria and so on.
From a science perspective as well. From a science perspective, how do you? What's that changed since you last visited?
Well, of course, even my last brief visit, being before LEP started, was I mean the program since then has been for me much more exciting than many things that went on before, and I've certainly followed the way that LEP did precision measurements on a standard model. I followed that very, very avidly, and obviously I'm looking forward to what LHC will do. About the visit itself, well, we had a strenuous first afternoon with CMS followed by Atlas. My impressions were, first of all, that the sheer scale of the detectors was overwhelming. It was, far more impressive than you get out of any photograph. I was also very impressed by the number of very tricky technical problems which people had to solve to get these things together at all, and the way in which they managed to organize the manufacture of components from other countries all over the world and get them to fit together. I think that's the building of it is really an impressive achievement. After that, we saw Alice on Saturday, and we still have to see LHCb before we leave this afternoon. Comparing the various detectors we saw and the organisations, the obvious thing to me was that Atlas was way ahead of the others in terms of public relations. CMS were also extremely impressive in terms of our interaction with them, but they didn't seem to be sort of reaching out so much in terms of publicity as the Atlas team does.
Can you take us back to when you made the discovery of the mechanism in terms of what the state of knowledge was at the time and what led you to discovering this mechanism, and also what the response was at that time?
Okay. Well, the state of knowledge. Well, it's more than just a state of knowledge. It's a state concerning the state of beliefs and different beliefs about how the theory should be done. The time was the early 60s, and it was a time when the successes of quantum electrodynamics were way in the past, and the techniques of quantum field theory, which had been spectacularly successful in quantum electrodynamics, seemed not to be working anywhere else. And there had also been indications that even quantum electrodynamics was ultimately a sick theory and couldn't be the whole story. This was the work of the Russian theorist Landau. So a lot of people gave up on this way of doing things and concentrated on what was called S-matrix theory, which was getting the most out of rather general principles without committing yourself to a very detailed theoretical model. So at the time that I started this work, it was a rather unfashionable thing to be interested in. Certainly this side of the Atlantic, the dominant interest was in using S-matrix theory. And across the Atlantic, in the United States, the West Coast was broadly S-matrix theorists, and the East Coast contained pockets of the old culture, with the influence of Julian Schwinger at Harvard, whose pupil, Shelley Glashow, is one of the authors of the work which was turned out to be successful, my colleagues thought I was a bit of an idiot. I got interested in it because I'd been puzzled about symmetries in particle physics. I mean, they're puzzling enough if they were good symmetries, but they weren't even good symmetries. They were very broken symmetries, and I got interested in the work of Nambu, Japanese-born American theorist, when it appeared in 1960-61, and I got interested in trying to avoid a difficulty which his type of theory, which was based on an analogy with the successful theory of superconductivity, there was a difficulty which seemed to prevent it from being actually useful, and that difficulty was the existence, the prediction of zero mass spinless particles, which, certainly if they occurred in the context of strong interaction physics, would result in stars radiating at a tremendous rate in a way on top of, extra to electromagnetic radiation. So it was essentially a mutual difficulty. And it was that difficulty which I saw how to evade in the very first short paper which I wrote. And the way that I saw of evading it was write down the very simplest model theory, which shows it happening, which is what became known as the Higgs model. And I mean that was within a week or so, well, maybe I shouldn't be telling this story in Geneva, but the story is that the first paper, which was a sort of negative thing, saying that that these proofs that there's a difficulty are not university valid. That was accepted by the editor of Physics Letters, who was based on CERN. The second one, which I thought was the more important bit of work showing how it actually works, is what became known as the Higgs mechanism, was rejected.
By the same editor? By the same editor?
By the same editor, yes. I was sharing an office with a colleague who was an S-matrix theorist who went off to CERN just after I did the work for the summer, and he came back and said, well, they didn't at CERN they didn't see that what you were talking about had much to do with particle physics. And so I then added on some additional paragraphs and sent it off across the Atlantic to the revised version to Physical Review Letters, who accepted it, and the referee I discovered later was Nambu. I mean, they had people who spoke the same language as me. But the mention of what became known as the Higgs boson was part of the extra which was added on, because I thought if they don't understand what this is, what relevance this has to particle physics, I'd better mention a few consequences. And I mentioned the existence of, in theories of this type, of what I call leftover massive spinless particles, at least one in any such theory, as a sort of indication of an experimental signature. And that was what was then labelled a Higgs boson.
I see. So the Higgs boson was not mentioned in the paper that you sent out to CERN?
The one which went to CERN didn't mention that, but I didn't send the second version to CERN because I thought, wait.